Okay, so for today, Antonio is going to finish up the Jupyter notebook from last time, and also addressing feed forward neural network. And I update everything over here, and also I hope he's having some time to try the convolutional neural network. Antonio, to you.
Okay, I'm gonna share my screen. All right. So today is the last official lecture, right? We are planning to have this paper discussion next Thursday. Although this is the plan, you guys by now know that I'm very bad with sticking to the plan, right? So I'm adding myself a little bit of a slack here. So if we don't finish convolutional neuronal networks, and based on the papers that you guys have sent me so far, I believe that's a topic of interest. I think that it is worth to cover it. So what I'm proposing is to perhaps sacrifice a little bit of the paper discussion lecture to potentially finish CNNs. And why is that? CNNs is like it's an important core component, right, of computer vision nowadays. And when you're talking about like geocomputing, big component of it is basically like satellite image or like remote sensing that can be considered some sort of imaging, right? Like basically spatial data. So I think it is worth to cover that in details. So I think that I might need to use a little bit of the next lecture for the sake of finishing CNN. And in this tutorial specifically, I cover one thing that I think it's extremely handy for people who are like going to be training several models, called weights and biases. Anyone here has heard of it? Weights and biases? No? Is this gonna be new to everyone? Okay, yeah. I think that's a really nice tool when you're faced with the situation that's like, I have to do hyperparameter search, and I have this one metric that I have to be keeping track of, which is like accuracy or sometimes like mean square error or so, right? But I don't have a systematic way of how to assess these models later on. So weights and bias gives you a really nice way to keep control of all the models that you have trained and to perform hyperparameter search at the same time. So like, I think that's very much worth the time of spending some extra minutes in the next lecture for that if needed. Okay, great. So the plan for today, all right, is to cover feed-forward neural networks. We already started talking about multi-layer perceptron in the previous lecture, although we didn't have time to actually like name things, right? We stopped at just the idea of like start concatenating perceptrons. We finally are gonna see how we can train these models, right? Like we have been very fortunate so far, which we only had one layer that had to actually learn weights, right? So you guys remember that there was just one linear layer. Now, what happens when you have to combine those, right? So like we had several perceptors. So like how do we combine them, and how we keep track of the changes in weights when you have like a stack of perceptrons, right? Some debugging tips, you're gonna learn that there is no like silver bullet with respect to training neural networks, but there are some clear guidelines, and I'm going to share those with you guys, right? We're going to see neural nets for the tree height data set, and then finally, we're going to get to CNNs. And hopefully, we get to at least half of it by the end of the lecture today, okay? Okay, quick recap. So we have seen perceptrons working individually, right? I have told you this story that like the perceptron is this one building block of neuronal networks. We discuss what type of laws the perceptron is trying to implement and why this is considered like not optimal hyperplan method of fitting a model to data, right? Although we're not really like interested in like optimal hyperplane, but any hyperplan that can solve a task, and we assign the regularization part to the ways how we can regularize a neuronal network, right? One key component of the perceptron was this activation function, which is this no linearity that's added to the output of the perceptron, right? And we have seen extensively that matching the activation function that's being used to the range and the distribution of your output is crucial component for you to be able to get a model that can fit at all your data, right? So we are not even just talking about like increasing capacity or performance of your model, but if you mess up with the activation function, you might even prevent the model from fitting to your data. So like it's very important to like pairing the activation function to the problem you're trying to address. We have discussed extensively like optimization methods, right? The basic component to all of them is the idea of first computing a gradient, right? Which is this partial derivatives of the with respect to all the weights that you have in your model, right? We have discussed the importance of this one hyperparameter, which is the learning rate, right? So like the learning rate is this multiplier that we have to the gradient that was computed, and essentially stands for like given the gradient now at this point tells us the direction in which we're going to move. The size of the step is the learning rate. So like bigger learning rate, bigger the step that you're taking, there are some risks associated to larger learning rates, right? As we saw here, for example. Where is that slide? Oh, I think I removed. But you guys remember that there was like a big zigzag going on when you had a large learning rate, right? Okay, great. So that was one of the risks, okay? So we saw that uh having this very complex problem is kind of like the ideal scenario. Like that's the dream of any like data scientist to have like something that looks like an actual ball, right? So people have implemented mechanisms to prevent you from getting stuck in local minimas, right? Local minima being the challenge that if you're keeping track of the gradient descent, by all means, local minima would be any point in a loss landscape that could be as complex as this one that we're observing here, right? Where the derivative is equal to zero, right? If that's the unique criteria that you're using to navigate your loss landscape, right? There are many places here that you would potentially have a gradient equal to zero. To address that, people have implemented other metrics, right? Other hyperparameters, essentially. One of them being the idea of this momentum, right? So like the momentum is this energy that's associated to like this ball that's rolling down like a hill, right? Or in our case, the points in which we are computing the gradients, that although the gradient is equal to zero, by all means, right? You still have one extra element of energy to the way how we're navigating the loss landscape, which is the momentum. And this kind of works towards the idea that basically you have some sort of like latency before you decide to stick to that local minima that you have found, right? So allows you to explore a little bit the neighborhood around that point of local minima that was identified. Now, with the advent that you have two hyperparameters to tune, right? The learning rate and the momentum beta. And of course, when you're talking about like finding these hyperparameters, it becomes a little sensitive. You have to like be doing this hyperparameter search, either with grid search or Bayesian search. And we have seen that sometimes it can be tricky, right? If you pick like a learning rate that's very large initially, for example, that might not allow you to converge, right? So like people have decided to look for ways how you can potentially reduce the impact of messing up big time on your hyperparameter choices, right? Some of them is this idea of adaptive learning. So like as you keep training, you update your learning rates, right, over time, based on the gradients that were computed throughout the process, right, of optimization. Ada grad essentially proposed that, but there was a huge issue with like the way how we're accumulating gradients to do this computation. If you guys recall, Ada grad compute stores the square of the gradients that have been computed throughout the training steps. So this usually converges to zero extremely fast, and you might get stuck in regions that are kind of suboptimal still, so like far away from your uh, uh, through local minima or like global minima, hopefully. So other methods came to address that, right? Which was the idea of adding this exponential decay average, which was proposed by RMS Prop and Adam, right? So Adam has all the components basically that have been introduced so far. It has the idea of a learning rate that's being uh, uh, adapted throughout the training steps, right? Based on these two quantities that are now the square of the gradients, right? Plus a momentum that's being added, right? So like it essentially combines the best features of each one of these optimizers. And therefore is my method of choice when I need to pick an optimizer. But like many of these optimizers, they have similar properties. Like usually the difference between them is essentially how fast they converge to these global minimums that we are looking for. Okay. Then we discuss when perception fails, right? So for example, like when we are no longer dealing with a linear problem, right? And I gave you like one extremely simple example there, the exclusive OR gate, right? So for example, in scenarios like these, when one single hyperplane can no longer solve the problem, one alternative is to start stacking perceptions, right? And that was essentially what we did there. We came to the conclusion together that if I could move from one single perception to two perceptions, I would have two separating hyperplanes that, if combined, they could solve the exclusive OR problem, right? And that's essentially the principle of increasing the dimensionality of a problem, right? We have seen that before with the kernel trick in support of vector machine. So this is the similar concept. But we do that essentially by increasing the number of neurons that we are working with and adding this intermediary layer, right, in this network now, because we are no longer dealing with a single unit, that now we're going to call the hidden layer. So now we have an input layer, a hidden layer, and an output layer. Okay. And now we can finally address problems that have a higher degree of complexity, which is because the way how we can address more complexity problems is as simple as increasing the complexity of the model that we're working with. That's why neuronal networks, they are what they are, right? Because it's extremely simple for us. Once you have breaking down how you can train a model like this, which is one of the goals of the class today, right? It's extremely simple to keep extrapolating this solution, right, to more and more complex problems, right? And this is extremely powerful. The last thing that we did in the end of the lecture last week, right, was the introduction of this little toy website that lets you play with different types of classification and regression problems. You can pick the type of data, right, that you'd like to classify or regress. And you can play with the architecture of these networks, right? Here we had the option to play with like number of hidden layers that you had, number of neurons that you had in these hidden layers, right? And if I recall it correctly, I think I left that as an assignment for you guys, right? Great. Uh, can anyone here share perhaps like one experiment that they did or something that they observed that they thought was cool, either like as a classification or a regression problem? Anyone would like to comment on their experiments? What type of data you used, like the architecture that you use?
Yeah, maybe I can show.
Yeah, yeah. I'm going to
Okay.
stop sharing and you can go ahead.
Um, okay. Do you see?
Yeah. Mm-hmm.
Yeah. This is like a screenshot. I try with the like a spiral cloud. I was trying to facing it. I found this kind of like a feature that fits well. The main thing is like I was like running also now with a different activation method. It was like how much the learning rate changing the output in this case, the reaching like the
Right.
as it showed the global minima this in this case of the prediction. one thing I like, it showed like suddenly was like the more hidden layer I had, the more I just like corrupt the whole prediction. There's like a finite number is not getting better if I add something. It was like
Right.
just like this method here that I tried with the tan h method. It goes to the prediction, but as soon as I add another hidden layer, it gets messed. It doesn't reach. It becomes like unstable. It started like doing I think it's like prediction. It gets worse
Right.
during the epochs.
Right. So there are
Sorry.
a couple of things, right? There are a couple of things here. Like, for example, your observation with respect to the learning rate, right?
Yeah.
So when you add hidden layers, right, and more nodes to these hidden layers, if we use a learning rate that's too small, right, this model might take way too many steps in order to converge, right?
Okay.
Keep in mind that the number of steps has to be closely tied to the gradients that you have, right? So for example, if you have like 10,000 steps, the gradients are relatively small, right? And your learning rate is also small, you see that the gradient is how we are updating to some extent, right? The gradient is one of the many components that goes into the calculation, how we're updating the weights.
Okay.
So what's happening? If you have small gradients, a bunch of steps, and small learning rate, the weights, they're not being updated as fast as they should, right? So what's going to happen is that this thing is going to get stuck in a local minima. So one of the things that you do, like in like neuronal networks and deep neuronal networks more specifically, is to start with a larger learning rate. So I think that's like the model that had the best performance for you was 10 to the minus 1, so 0.1 for learning rate, right?
This one?
No, I think it was 0.1, I think. You're using 10 to the minus 3 right now, so that's even smaller. Yeah.
Yeah. And yeah, I started like figuring out some like instabilities.
Right.
Yeah. So
like maybe slightly smaller, but you see that like this thing, it's already showing like good performance in terms of classification, right? So like the borders of this hyperplane, they're not being very well defined, right? As you can see, like there is all these fluctuations there, but by all means, the bulk of the data, it's already being classified correctly.
Okay.
Right?
Okay.
So it's
I was
a matter
not
of
sure
like
about this. Yeah.
setting. Yeah.
So
No,
like
a little bit of instability is not the end of the word. Yeah.
So like the learning rate should be like facing the like the complexity of the hidden layers. The more hidden layers we add, the more learning rate should be higher in this case, because it's longer path to reach the
right.
Yeah. Okay.
Yeah. So like I think I very briefly mentioned that, right? So like for example, the classification performance for your model here, right? It's basically pretty good already, right?
Okay.
The parts where you see these fluctuations in placement of the hyperplane, right? They're not even in the data anymore. You see that?
Okay. Yeah.
So like by all means, the performance of your model is changing very, very little at that point, right? But if you want to see a model that's very stable and converged, right? What you can do sometimes is to stop. So press pause, change the learning rate to like a smaller number now. Yeah. And keep going.
Oh, sorry.
Oh, it's reset. Okay. Yeah, it's okay. It's okay.
Sorry. Okay.
But no, yeah, it's fine. It's fine. But like this trick that we just did here, it's essentially what people call in machine learning the warm-up, right?
Okay.
So like,
okay.
Yeah. So
that was like a part I did. Yeah. So it's like basically the first part is starting learn rate, and then okay. But
yeah, and the cool thing is that tricks like these, they essentially allowed you to train extremely large models, right? Such as large language models. like a model like ChatGPT can only be trained because we are using tricks like that. Otherwise, because like we're talking about models that have billions of parameters, right?
Yeah.
How many parameters do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. We have 16
Yeah,
parameters.
16. Yeah.
We're talking about a model that has
Billion.
like
Yeah.
50 billion parameters. Yeah?
Yeah.
So it's very important to find these tricks.
Okay.
Mhm.
But like the threshold to define where the warm-up stops, and then we can go with a smaller learning rate. We should like find with like trials.
Yeah, so there are a few things that you can use, right? So for example, you see that there is this very fast drop, right?
Yeah. Because
About
I also
like
try in different runs to
right,
smoothen this. Yeah.
right. So like after you have gone through the elbow, right? What you don't want is to have a model that essentially does that, right? Because when you're doing this, consider that this is the error, right?
Yeah.
So like the gradient in our case, it's computed as being the partial derivative, right, of the error. So it's error by the weights, right? And
Yeah.
if these little steps that you have here, right, they don't represent a significant drop in error, that means
Yeah.
that your gradient by itself is not changing much, right?
Okay.
So like the rate in which you're updating the weights is too small, right? And if these steps they become smaller and smaller with a learning rate that's too small, so like this product is way too small. And this is exactly the product that defines stochastic gradient, basically, right? So like this thing could get stuck.
I also like
The
faced
pity.
here this kind of like bouncing back or a small plateau, this like the local minimum, then it drops to the
Mm-hmm.
global minimum, I think, right?
Right,
This
right.
case. Yeah, okay.
But this was just like a little
Yeah, it was
deceleration of
different.
the
I tried
gradients.
some
Like, yeah.
differences. I try
Mm-hmm.
to reach the same like result, but with different parameters. In this case, it was like
Yeah.
more like yeah, vertical the drop.
Yeah. This was a pretty nice drop there. Nice.
Okay.
Okay, maybe we can
Okay.
just see one more case, like one more person would like to share their experiments. Thanks a lot for sharing ours,
No
Silverio.
problem.
Yeah. Anyone else?
Well, maybe I can share.
Ah, yeah, awesome. Yeah.
But well, I don't try really complicated things. But wait, can I
Mm-hmm.
share
Yeah. While you
it?
open yours, let me go get more
Okay.
coffee. Oh my.
Yeah. So I just oh, okay. I will wait.
It's still 7 o'clock over there.
It's 7 o'clock. I just woke up. Yeah. Okay, go ahead.
Yeah, so I just set up this well circle thing, and then yeah, so I first try different activation functions, and only tangent and tangent edge and ReLU can really help here, because well, if I rerun this, it kind of, yeah, no, not really, but I have to maybe add more layers here, and then it's fine. Well, sort of, but if it's linear or sigma mode, yeah, it is not doing well, not
So
coming to the
I just noticed one thing. You're using 3 neurons in the output, right?
yes.
Why do you need 3 neurons if it's a binary classification?
Three, two,
Even one, right? If it's a
yeah,
binary classification, you just need the output to be either 0 or 1, right?
yeah.
So
I
like
guess I
now,
was playing with different output, and then yeah,
I
I
see.
just forgot to change back. Yeah, but then anyway, it
Right,
is not giving good result with these two, and but I think with tangent
right.
edge is doing quite well.
It and why do you think it's not working for sigmoid?
Um, because it's not um yeah, it doesn't well, it's not like only above certain numbers, so it's covers from 6 minus 6 to 6. So
So two things, right? So like you're saying that your problem is oh, just a second. It's a 2D problem, right? So what you're observing here, can you scroll down just a little bit?
Yeah.
Yeah, there. So what you're observing here would be like x1 and x2 here, right? So this is the range of your features, right? So like you're dealing with a 2D system, right? Now, what's the actual range of your output? So this is the range right here, right? So like your data is mapped between -1 and 1.
Yeah.
Right? If you pick a sigmoid, what's the output? What's the range of your output?
It's 0, 1.
It's 0, 1, right? So like you'd be
Yeah.
able to fit stuff that's just in this range.
Yeah.
Like when you run the sigmoid, right? You remember that everything here was orange. So like that means that everything was kind of like in these spots right here.
Yeah.
Right. So like you don't want that.
Yeah.
So that's the reason why only the hyperbolic tangent would work, right? So like at least that part we got covered. Now with respect to the output, right? I said, oh, you're just dealing with a binary classification, right? For most of the problems here, I think they can mostly be dealt with as like binary classification problems. So like, although you have the option to increase the number of neurons in the output, you don't actually need that, right? So like you're increasing the complexity, but in the end, probably just one of these neurons are actually doing classification for you. The others, they are there. They're still being fine-tuned, but they're not really doing anything. Okay? But nice, yeah, it's nice that you managed to find architecture that works for you. Can you just change the number of neurons in the hidden layer? Let's see what happens.
In the layers here, or
Yeah, in the middle. Yeah.
with more, or
Yeah, more. Okay. So Saverio, did you see like this first drop, like how slow it was? Right?
Yeah.
So like this model converged very nicely, right? Because the learning rate is small. So like you see that's very stable, very controlled decay, right? But there was that several number of epochs, like in this little part here, right? Where the gradient was kind of small, right? So like the dropping here was relatively small. So can you repeat this experiment with a larger learning rate? So like increase it by one number there. Yeah. Let's see 0.03 first. Yeah.
and then reset.
Yeah, reset. Okay, that was a little faster. You can go even bigger. Let's say 0.1 now. Oh, that was too much. Okay, so 0.03 seems to be the sweet spot there. Okay. Nice.
Yeah.
But you see that like even with 0.1, right? Didn't look like it was completely stuck. So like do 0.1 again. Let's see.
0.1. Okay.
Yeah. Oh, yeah. It was showing some signs of getting stuck, right? And then it very quickly managed to escape that local minima, right? The hyperplanes, they're not beautiful, right? They're kind of like a star shape in this case, but they're definitely doing well. And notice that, can you zoom in a little bit in the plot?
Zoom in?
Yeah, zoom in. Yeah, yeah, yeah. Look at this thing. Like this data was kind of noisy, right?
Yeah,
But
that's
because
actually my question, because I was trying to, really like group them nicely, like not including them in this blue
Oh,
hyperplane.
no. It's good to have a little bit of noise because these are realistic data, right? Like
Yeah.
usually you do have some faulty readings, right? Some like sensors that didn't work out well, right? So it's nice to include that as well. When you had the circle hyperplane, right? I think those points that are being misclassified. So like here actually looks like this is becoming a little hard coded, right? But it's performing well. Can you show the test data? So click on this button down here, show the test data. Okay. Yeah, there are a couple of points there that seems to be misclassified, right? So for example,
Yeah.
there is this orange one that got inside, right? And what's happening here? So like the test data for the training data, it was working perfectly well, right? But like now that we add the test data, we're seeing some things that are falling in the wrong place, right? So what's happening here? Do you guys notice this one thing here on the corner?
Is it an overfitting?
It's overfitting. Yeah. So these models start to overfit. What can you do to potentially address this is to add some regularization. I see that you're not using any there, right? So like
Yeah.
maybe you might want to add a regularization there. Try L2.
Two.
Yeah.
Oh. It is not
Okay.
convolution.
I think it's like, for me, it was the regularization rate. It does the same issue for me.
Oh,
Here.
okay. So change the, yeah. Yeah. 10, it's a little too much. So try something a little smaller. Yeah. Even smaller, perhaps. 10 to the -3. Yeah, 0.01. Yeah, yeah. This one, let's see. There we go. Didn't entirely solve the problem. So like we still see that there is some misclassification there. Maybe like a smaller learning rate now. Yeah. Yeah, 0.01. Let's see. Okay. Yeah. C'est la vie. You can't perfect classification is an idealistic scenario, but okay.
Yeah.
But
But
by all
then
means,
which one's better? Like, is it better to have this more rounded shape? So, it's not maybe overfitting, or no, if
right.
it's with start shape, then it's maybe, covering the training data, but maybe it won't cover the testing data, right?
Right. When you have shapes that are way too complicated, right? They are going through exactly the training set, right? I usually see that even if overfitting is not happening for your held out test set, right? I still see that as a potential for generalization to truly unseen data later on, right? Because shapes that are just too specific, right? That starts showing that this model is getting way too trained in that specific data, right? And like these complex shapes, usually they're not really realistic, right? So I would give preference for like smoother boundaries, like a little closer to what we have now.
Yeah.
I think this is healthier overall, as in terms of like finding like the rationale for separating classes, for example. So like I give preference to smoother shapes.
Yeah. Okay. Yeah. Thanks.
Yeah, thank you for sharing that. I think maybe we can stop here and start with the content for today. But thank you so much, guys, for sharing your experiments. I think this was a nice learning experience there. Let me share my slides. Okay. Did you guys like playing with this little toy example there? Yeah. You can learn a lot with respect to like how these hyperparameters are controlling these separating hyperplanes that we're training here. And we are going to bring a lot of these ideas now to the way how we're designing the neuronal networks. Okay. Very well. Now we have extensively seen, right, like how this scaling rule seems to help tackling more complex problems, right? So I haven't really like given name to things yet, right? So we went from using a single perceptron, right, which was this one linear unity, right, which you can remove its linearity by adding one activation function at its output, right? the act of stacking these perceptions, as you can intuit by now, right? It's essentially what originates the idea of multi-layer perception, where this multilinearity, right? In this case, not linearity, but like this multi-layer idea essentially stands for the idea of introducing elements or these unities also in intermediary layers of this neuronal network, right? And as you have seen so far, right? Adding these hidden layers essentially allow you to take the problem from its original dimensionality to a higher dimensional space, which can allow you to properly find this new data dimensionality that's going to allow you to perform the classification properly, right? Which is the same concept that we have used for supported vector machine when we said that there was this kernel trick that you can use to increase dimensionality and make the classification problem easier, right? Now we have one challenge, right? So like the challenge is what we had before, right, was just, let me turn on this, was input, right, which was being combined to one single element, right, going through an activation function and then output, right? This, although we had this activation function, right, this nonlinear component, it was extremely simple for us to be able to see what was the impact of changing the weights, right, with respect to the inputs that we had, and what was the influence in the output, right? So that was relatively straightforward because the function that's being implemented here is still f of xw, right? Where this f of x is as simple as just having this one dot product of the weights that we have times the features of the input, right? But now we have all these intermediary layers, right? All these hidden layers here. So the impact in the output, it is many degrees of separation from the actual input now, right? So detecting what's the influence of these weights and also these weights in the output becomes a no trivial task, okay? So now we're going to see how we can leverage the same tricks that we have used so far, this idea of computing gradients, but now with deeper neuronal networks, right? And I'm going to tell you ahead that's essentially breaking down how you can actually solve this, right? Is essentially what took us out of the deep learning or neuronal networks winter, right? Because I think I have mentioned to you guys that all these ideas of like perceptions is everything, right? Perceptions and multilayer perceptions, they are ideas that are as old as the 60s, right? But even though that's the fact, like machine learning, as we know nowadays, is something quite recent, right? And I had one plot that essentially used to show the usage of the word machine learning and deep neural networks over time, right? There is one bump around the 60. Then people realize that, oh my God, yeah, once we start like scaling up perceptions, right, to solve more interesting problems for us, these things, they become extremely difficult to train, right? And then people are like, oh, this is way too complicated. And then what happened is that they went back to support the reactive machine, right? Because like, oh, this is much easier to train, right? For the simplicity of like how you can fine tune these models, right? And like, because it's easier to understand, people went back to support the vector machine, and support the vector machine picked up a lot of steam until the one guy who like nowadays in the media is called the godfather of machine learning, Jeff Hinton. He found out how we can actually train this thing using one trick that I don't know if I have mentioned already, but it's go by the name backpropagation. Okay, so backpropagation essentially taught us how we can effectively use the idea of gradients to train deep neuronal networks. And that's what we're going to start looking at right now. Okay, before we do that, it's important for us to rename things, right? So before, what we had was this f of x, as I have written in the previous slide, right? That's now is used to be what we were calling our model, right? And then this f of x was compared to our y, where y was the ground truth, right? And then by comparing these two of them, right, we would run some sort of, oh, not a mess, but like MSC, right? That was conditioning what was by how far off we were to our targets, right? So now let's rename things. So for the purpose of like making this a bit more digestible, right? We're gonna move from this vector representation that we had for the weights, right? So like, so until now we're representing the weights as a vector all the way to Wn, right? Now, because we have several layers, right? If you're trying to understand the relationship between any neuron in the hidden layer and any neuron in the input layer, we're gonna turn that now to a matrix, right? So now we're gonna have a matrix. Two all the way there, and here's gonna be n by m, right? Where n would be the number of neurons that you have in the input layer, and m is the number of neurons that you have in your second layer, right? Although I'm talking about input layer and second layer, right? This can be very easily extrapolated to any intermediary layer, right? So like this could be any neuron that is in the layer L, for example, right? So let's say that this is the layer L, and this is the layer L plus 1, right? So like this nomenclature that you have here on the top right can be applied to any neuron in any degree in these hidden layers as well, right? Just as we had before, we are still gonna have the bias. So like the bias is still something that, although we don't explicitly include, so for example, I was saying that was just f of x until now, right? But you can very easily say that there you have one extra term, which is the b, which is a bias that gets added to each one of these neurons as well, right? This bias, it can be take a form of a single value when you're talking about the perceptron, right? Or now, because now we have many neurons to many neurons, it takes the format of a vector as well. Okay, so like that's gonna be B1, B2, and so on. Okay. All right. Now, just as we did before, right? If you're taking one neuron here and this one neuron is getting like many inputs, right? After I have summed all the inputs that are coming to this neuron, right? There was one element here that was still going to transform the summed input that this neuron is receiving, right? Which one was this? Which element comes here?
So the activation function?
Correct, is the activation function, right? So like there is the activation function that comes here. So the activation function in our case, right? You see that this is the weighted sum, right? Of the inputs that are coming to any given neuron, right? After we have done, we're gonna call the activation function the sigma. So like that's the sigma over the weighted average of the inputs. So the output of any given neuron at this point, we're gonna call this A prime, okay? So that's the output after we have done the weighted average and the nonlinearity or the activation function, okay? So this here now describes what's the activity, right? Or like the output for any given neuron. So like now this is gonna have one index here that essentially stands for like which layer, in which layer you are, and which neuron we are talking about, okay? Any questions with respect to nomenclature? No? Okay. This is important because that's essentially how we're going to describe the whole process on how we're referring to like single units in this neural network from now on. Okay. Yes. Mm-hmm.
I have a question
yeah.
where you mentioned the metrics. So it seems like this like the suffix ij, so that would be between two layers, right? So if you have 3 layers,
Right.
that means there will be 2 Ws.
Right, right. So this is the connection of any layer L, right? And the layer L plus 1. So like that's 2 successive layers in this neuronal network. So like, let's say that you have 3 layers, you have at least 2 Ws, right?
Okay.
Okay. We had one more question.
Yeah. There was a question concerning the activation function. In this case, we are as soon as we adding like hidden layers, so we adding complexity to the net. We can even nest activation function in between every hidden layers. Every neuron can be also their relative activation function. Like is even more complicating the I think the geometry of the hyperplanes.
That's correct.
Is right. That's correct. Okay.
Right, that's correct. There is one observation, right? So we have a set from which we can choose an activation function from, right? So we have discussed the hyperbolic tangent, sigmoid, ReLU, and so, right? In theory, you could be using any of them, right? Like in your hidden layer. Like I'm not even going to discuss the output anymore because now we know that the activation function that we use the output should be conditioned to what are we conditioning the activation function of our output to? How do we pick the activation function of the output?
Like we can choose it based on the data we are like going to train.
Exactly, based on the range of the data that we're trying to model, right? So like that's essentially conditioned by our y in this case, right? So we could be using like a ReLU, we could be using sigmoid, right? Even hyperbolic tangent. But there is one guideline that was given to us by our godfather, right? Which is the usage of ReLUs or ILUs. So like we have discussed ReLU extensively, right? And we have discussed ILU very briefly. So like the ILU is this activation function that was not necessarily 0 for negative values, right? But actually it was slightly negative, right? But plateaued still, but slightly negative. And why was this better, right? For example, you guys remember that I have beaten pretty hard on the idea that having things that are discontinuous, they might be bad for training, right? So like, although this works, right? Jeff Hinton said that these might bring some instabilities, right? And actually turning this activation function in something that is smoother, right? And therefore has a better distribution in terms of like fluctuations of weights over time. He said that ILU actually helps, right? Most of my models, I still use ReLU, right? But if you actually go see the code of these modern machine learning methods that are coming out nowadays, most of them are using ILU now, right? So I believe this helps with stability of training overall. So by default, either pick ReLU or ILU. Sigmoid hyperbolic tangents, they could be a choice, right? But they are less popular in terms of like intermediary layers. So like you don't use those for hidden layers overall. I also see leaky ReLU once in a while, right? But apparently these two are kind of equivalent. So it's just the idea that even if you're predicting something that's like in the negative range, right? Not everything that's in this range has exactly the same should have exactly the same end factor, right? If I'm making a mistake, let's say that's -1, right? I should not be equating that to -20, right? So essentially the idea is like, by how far off am I in a spectrum, right? So some of these help. In general, either you pick ILU or ReLU. Myself, I still use ReLU quite often. Okay, but never this other tool. Okay, again, this is guidelines, so like things that people have gone through and seems to help. But by all means, that's something that you should try. Okay, any other questions?
And this is true for both regression classification problems.
Yes. That's in terms of like architecture of neuronal networks in general. Like the middle part, the hidden layers, right? It's essentially like how you navigate lost landscapes, right? The output is conditioned by like what's the range of the data that we're working with, and the input, basically there is very little to be done at the input layer, right? Besides like pre-processing of the data. So like making sure that your the range of your features, they are normalized, right? All the things that we have been doing since we started working with support vector machine. So there is no real novelty there. Like the hidden layers, they are like how you increase dimensionality of the problem, right? And the output is conditioned to the range of your output data, right?
Yeah, just
So
another.
regardless of classification, yes.
Sorry, like the relation between the running epochs when we are like doing even more like reiteration between the net, and the start of the diverging between the loss of the train and the test. I start seeing like in some kind of models they start to diverge with like over 2000 epochs and so on. There's like we should put some stop into certain epoch, because I don't think we have not reached yet the global minima. I think we reached the solution of the model. I think the proper model for fitting the data, but I don't get it why it's starting to diverge.
Right. So a little bit of divergency, right? It's expected. Because in the end of the day, this model is being fine-tuned on the training set, right? The test set is just like a valid something that you're using for inference and seeing how your model is performing on like a hypothetically held out data set, how it's going to generalize new data, right? So when you see training curves that look like this, let's put one here, and then you have the second one, that's the test set, right? Most often, this is what you're going to see, right? The ideal case, these two would be overlapping 100%. So like, let's say that you have like a vast amount of data, right? So whatever you're learning for your training set is going to apply very well to the test set as well, right? So that would be the idea of generalization. But let's say that you do a split of 80% training, right? Versus 20% test. It's more likely that this 80% includes like a better distribution than this 20%. So like you might have some outliers, right? Some stuff that's just not gonna work like in this 20%, depending on how big is your data, right? So little gaps like these, they're expected, right? What you don't want to see, right, is something that's gonna look like this. Let me delete this one. Something that's gonna look like this. Then you have like your training curve, and you have your test set that's behaving like this, right? Because this means that your model is getting over specialized on your training set, right? And at the cost of increasing this gap, which essentially stands for like, as I get better at the training set, I'm sacrificing my performance on the test set. So this is overfitting. So like here you should stop.
Okay.
Like when this gap starts to increase right here, you should stop. But in the case that you have just like a constant gap, like two lines running parallel, you can allow it to train for longer. So like that's not necessarily a big deal.
Yeah, because there was like a gap, but it was like increasing, not that steep.
Yeah.
Yeah. Okay. So it's overfitting
Right.
in that case. Okay. Thank you.
Okay. Okay. Any other questions on this? Okay, so let's move on. So, okay, I have told you that backpropagation that is now allowing us to keep track of what's the end result of updating these weights, right? but I haven't told you how we extrapolate what we have seen in terms of gradient calculation, right? Now to multi-layer perceptron. So how is that gonna take place? And let me anticipate here that this is something that's unnecessarily complicated, right? And we are not going to discuss this in a lot of details because this is by no means a math course, right? Back propagation is something that usually I talk to my students, right, over the span of like 2 weeks. And sometimes you get to the end of the semester, people don't fully comprehend this yet. So like, I don't want you guys to like, oh, I don't understand this. So like, let's just spend the rest of the lecture on this. Like, no, this is not the goal, right? I just want to show you like how these things are calculated. Okay, so what we have seen so far, right, is that at the output, right, of this model, now we still compute the error the same way how we were doing before, right? We have said that we have the activation. So A here, right, these A's, they are after our last activation function, right? So this, after we have gone through the nonlinearity, we are comparing that to our target, right? So like that's our actual y, right? We are computing the difference and squaring this. So this is our good old friend MSC going on right here, right? Now, okay. So for any given neuron, right? So like, let's say right here before the activation function, we have the weighted sum of the things that are coming from the previous layer, right? So you see that like here, I would have the W's, WLs, right? Like in all these guys here, and they're being multiplied by the things that are in the previous layer, right? So like, let's say that this is L, so these would be L minus 1, right? So like I'm combining all the things that are coming from the previous layer, right? Multiplying by these sets of weights and adding some bias there, right? Now, all of these, right, which like I'm calling Z for the sake of simplicity, goes inside of this sigma function. The sigma function represents my activation function. Okay? All good here? Okay. And then to simplify this even further, right? Like I'm gonna combine this nomenclature and the way how I represent the output of any neuron after I have done the weighted sum plus the activation function. So I can refer to this either as the A, right? The same way how I'm referring to, or simply as sigma Z. Okay, so that's just the notation for these guys here. Now the challenge comes to what are we aiming for, right? So like, what are we looking for? You guys remember that the gradients, right, that I'm looking for, they should have this shape. Should be the partial derivative of error with respect to weights, right? But which weights? All of them. So like all these weights that are like everywhere here, right? I don't have a straightforward way of doing that, right? Because for me to be able to do this, I have to be considering what's the error, right? What's the contribution of each one of these weights, right? To the error that's all the way here, okay? So that's not a straightforward to do, straightforward thing to. That's not a straightforward thing to do, right? So I have to use these little tricks in the intermediary layers, right? What I can compute, right, is the contribution of any output that's coming from the previous layers, right, to the quantity that I'm measuring here, right, in these little places here. So what I'm gonna do is to find a proxy for the way how my error intermediary layers is contributing to the final error in the output layer, right? And I do that by computing this delta quantity that you're seeing over here. So what this delta is doing is to compute the error in the output layer with respect to these intermediary outputs that I'm getting here, okay? How can we do that, right? Because we also don't have this quantity like ready to be used, right? But what I do have is the contribution of this activation function to the error, okay? And I also have this one quantity over here, right? Why do I have that? This, we just have the formula that we just calculated together, right? So like, okay, this is accessible to me. And this is essentially a parameter that is included in the calculation of this output, you see? So I have this guy and I have this guy. So that's great. So these I can very easily calculate because I have the expression for that, right? I can summarize this quantity over here as being pure and simple the derivative of this guy, right, with respect to the z, right? So I can summarize that as being this expression here now. Any questions with respect to that? So like this goes by a name, so like that's the chain rule, right? If you have done calculus 1, you have heard of that at some point in life, right? But essentially what it stands for is like, I'm trying to compute this quantity here, the error with respect to the weights. I don't have that, right? But what I do have, it's these intermediary quantities that we are describing here, right? So like I can use these things that I do have as a proxy for the thing that I'm aiming for. Okay, so that's the overall idea. These can be extrapolated to the intermediary layers as well. So like we keep like doing this streak over and over again, right? Which I'm not gonna go over that with you guys because otherwise we're going to spend the next hour doing so, right? But there are great books that are gonna break this down for you, right? What I hope you guys believe me at this point is that if you keep doing this trick over and over again for all the layers that you have in this neural network, eventually you're going to stumble upon something that looks like this here in the bottom, right? Which are going to be all quantities that I do have access to, right? And therefore, I can know precisely what's the contribution of any given weight to the overall error of my network, which was the initial goal. And this is by definition now our gradient, right? So like that was exactly the quantity that we wanted to find. Okay. Now, if you want to understand how backpropagation works, we can discuss that offline. And like Jeff Hinton has really nice books that describe this step by step. But to our purpose here, we are not going to get in more detail than this. Okay. Any questions here?
That's clear.
Okay. Well, I'm gonna wait one more second here in case anyone has any burning question. And I recharge my coffee.
Just
Okay,
one
so-
question about like the differences between forward and back propagation, like the main differences, and why it's more powerful to solve this multi-layer problem.
So the difference between the forward and the back propagation is essentially like the direction in which you're computing these contributions, right? The forward process is extremely simple, right? Because the forward process essentially stands for like doing these calculations in this direction. Doing the calculations in this direction, they are as simple as just computing these quantities here, right? So like it's essentially getting what's coming from the previous layer, right? Multiplying by the weights of my current layer and adding some bias. By all means, this is the forward propagation, right? Now, the back propagation is essentially inferring by how much these weights are impacting my final output. So that's back propagation, is finding these quantities, which are the premise for computing gradients in our case. You see the difference?
Yeah, that's
So like when you're talking about back propagation, we are looking for this quantity now, which is this guy over here. The forward is just how information is propagating from left to right in our network. This guy here is essentially inferring how things are behaving in this direction.
Yeah. And why we need these to find a solution for the multi-layer? Like the forward one is not cannot
Right.
serve here. Yeah.
Yeah, but like for us to be able to train the model, right? we are looking for understanding how small changes in the weights, right, the impact on our error. Because what we're trying to do is to minimize our error, right? When we minimize the error, that means that we have a model that's functional, that's doing the classification with a small error margin, right? Is performing a regression with a small error margin, right? What we're trying to understand is how we can leverage the information of error, right? This quantity over here, how we can leverage our information of error for any given set of weights. So we can change the weights, right? To minimize the error. So this is the same rationale that we have been using so far. It's always like I do an inference with my current weights. I see how far off I am, and I change it a little bit based on by how much it's changing. I know if I should keep like changing the weights in one direction or the other, which is the same that we are doing over here. Over here, right? So like these are the gradients that we're chasing. So like every time that we have a new arrow, that's like the direction of the gradient, right? We use this information of the direction of the gradient by how much the error is changing to fine tune the weight so we can keep navigating towards the region in this loss landscape that is the minima, right? So like, I hope all these pieces, they're coming together in our minds at this point.
Yeah. Yes.
Oh, okay, great. But yeah, good question. It's very important to clarify that.
Thanks. That's clear. Thanks.
Yeah. Once this model is trained, by all means, doing inference is just like a forward pass, right? So like every time that you say, okay, I have a trained model, I just want to do an inference. Those are forward passes that we're doing with this model, right? We no longer have the need of back propagating anymore. The back propagation is just during training. And perhaps that's a good time to do a quiz. Is there anything else that I need to cover here? Oh, yeah.
I have a quick question, actually.
Yeah, yes.
So can you then say that, like, for example, the weights between the input and the first hidden layer, it would in fact tell you how much or which parameter is more relevant for the results then? Like looking at the weights or like the weightage of the weights that you get?
Okay, so the
Because
question
I've
is,
seen in some papers, like I didn't get it that point of time, but I'm just thinking.
So you're asking if I can use the magnitude of these weights to infer the relative importance of features.
Yeah, exactly. Yeah.
Yeah, absolutely. You can do that. There is just one trick, right? Notice that the magnitude of the weights here, right, in this layer, they are not the final contribution for your classification performance there, right? These weights, they only contribute to the performance of these neurons. Right? So if you want to do like feature importance analysis, you have to see what's the contribution of all these weights, right, to the final classification. So when you're doing that, you need to include all these guys. By all means, this is back propagation again. So you're back propagating your class or like the value that you obtained all the way back to the input. So you can assess the importance of these features. And good that you're asking for that, because that's one thing that I'm going to cover on the CNN topic. I'm going to show you how you can do feature importance analysis, but on CNNs.
Okay.
Which I think it's cooler because then you will actually have a visual, you know? So for example, if you're trying to deal with segmentation, which apparently a bunch of people have like interest in segmentation based on the papers you guys sent. That's one way how you can do segmentation is by assessing the link between features. In our case, when you're dealing with images, those are like pixels in their specific values in specific positions, right? With respect to the class that you have in that given image. Okay? No, great questions. Yeah, very good. Any other question before I move on? Okay, kind of running out of time as usual. So let's move on.
Maybe one question, if I
Yes.
may, regarding the initialization of the parameters.
Mm-hmm.
Uh,
Yeah,
how-
so
yeah.
yeah, go ahead. Yeah, you can finish your question.
Yeah. Is there any technique to use for the initialization? Because sometimes, because I think that is a very a crucial element for the
Absolutely,
optimization.
yeah.
Yeah.
It is very important, the initialization. Uh, what I'm gonna say is that the default initialization is usually a uniform distribution. So like all the weights, they are like basically uniform distributed, right? People have noticed that the initialization usually plays a role on how fast you converge to the solution, right? Like having a bad initialization does not prevent you from finding the solution at all. At least that hasn't been described as being like a real deal breaker, right? So proper initialization helps with convergency, but doesn't necessarily prevent you from finding the optimal point, right? That you could find eventually. So most often I initialize things using the default, which is like uniform distribution. I have done small changes in terms of initialization when I'm dealing with extremely large neuronal networks. So like when I'm training like foundation models, right? I initialize that slightly different based on like these recipes that were released by OpenAI, right? So like when I'm training a large language model, I initialize the way how they initialize things. So like there are different ways of initializing. So like you're gonna learn about like Xavier, normal distribution, like which are all these funky distributions for initialization, but they never prevented me from finding the same solution in the end, right? So like I'm gonna leave that as like, yeah, there are recommendations according to what's the model that you're training, but that doesn't seem to be a real deal breaker. Okay.
Thank you.
Any other question? Okay, so let's move on then. We can have a little break in 20 minutes. All right, so we have discussed how we can train these neural networks, right? Using these concepts of backpropagation that now we have extrapolated to multi-layer perceptron, right? So like before, it was very easy for us to just discuss the training process in terms of just gradients, right? But now we have to propagate this information throughout all the layers. So like that's why when we're talking about gradients in terms of neural networks, now we are usually talking about backpropagation, right? Very well. Before was very simple for us to be able to regularize these models, right? Remember that one of the things that we were doing before was to penalize the magnitude of these weights, right? By saying that we are trying to minimize the square of these norms plus something that was like the actual loss, right? So like the square of these weights, I think I said the square of the loss, that's not the right, right? So it's the square of the weights of the separating hyperplane that you're trying to find, or the plane that's defining the position of this regressor, right? That was very simple to do. Why? Because this was a vector. So I can compute the norm of a vector, right? Now we no longer have a vector. In fact, this is a stack of matrices now, right? So because like, as we have defined, every between every two layers, I have a yj, right? So I have a bunch of those. So like now I have this for layer one, I have this for layer two, and so, right? So like I can no longer just use this simplistic trick. What people experimentally have found to be a proxy for that, right, is because what you're trying to achieve, right? We are trying to ensure that for any inputs that I have, right, and I'm trying to compute an output, all I'm trying to make sure is that in the ideal scenario, both features, they're going to be considered as like equally valuable, at least in the beginning, right? Equally valuable. So I have some degree of redundancy between these features, even if they're like highly correlated, right? I want to be paying attention to both because sometimes one of these are corrupted, right? So like I still can rely on the second one to make my prediction, right? Okay, doing this by penalizing the square of the weights is no longer doable with neuronal networks, right? Although you can still add like L square regularization to the weights, which is one of the parameters that we had in that toy example, right? So like what's the weight that I'm assigning to the L2, right? So like that was one of, it's still a thing. You can still do that, right? But this is not sufficient. So what people have noticed that helps to address this type of problem is to eventually drop the usage of some nodes, right? So for example, here we have a standard neuronal network, right? Here we have the input. This information is traveling in this direction, right? And here we have our output, okay? For me to enforce that all these these nodes, they are paid attention to, right? What I do is to eventually remove some of these nodes, right? So in every new training step, right, I change the nodes that are being used to perform a calculation, right? For example, if we are dealing with an image, right? So let's say that we have an image there. Those are the pixels, okay? I'm gonna break this image into a vector now. So like I'm linearizing this whole thing, right? And now I'm gonna pass that as the input to this neuronal network, okay? What would be the equivalent of doing that is that although, let's say that I have like a soccer ball here, right? Although I have many pixels within the soccer ball, right? That could be used to classify that as being a ball at all, right? I don't want to have just 1 or 2 pixels within the ball that actually describes this as being a ball, right? Because there is information that's included in this whole area, right? So every time that I do a pass, I just use few of these pixels to make a prediction, right? And the consequence of doing so is that eventually I I assign importance to all the pixels that are included in that area, right? And they all contribute to my final prediction, okay? And therefore, because now I'm enforcing the distribution of this importance, I achieve something that's closer to what we're describing up here, right? Which was the ideal scenario for like having a equally balanced future importance, okay? This is conditioned by a probability of this node being present in every training step, right? So like every time that I start a neuronal network, right? One thing that I can set is this one quantity that we call the dropout. The dropout, the parameter of the dropout is this p, which is like the probability of this node being present, right? So if I say that like this is going to be a p of like 50%, so like every time that I do a new pass, there is a probability of 50% that this node is going to get removed, okay? After I have done the training pass, right, and I want to run inference, I no longer want to run inference with just like few of the nodes, right? I don't want to run inference with this extremely scattered, like sparse version of my neuronal network. I want to run inference with the full network, right? So when I do inference, all these nodes are present every time, right? I hope you guys remember that when you're doing the training, right, on PyTorch, we had 2 flags that I said are extremely important to control. One of them is model dot train and model dot eval. When you're doing model train, you say, okay, I want all these regularizations to be applied, right? All the regularizations that I have included. So for example, dropout is going to be included. When I change the flag of this model to eval, I no longer do this, right? So like I say, all these things, all these nodes I would like to be included. So that's one of the many things that change the changing to evaluation mode is going to change in terms of like how you do a forward pass as well, right? On top of that, we also have the torch no grad. That's like telling you if you should be accumulating gradients when you do the pass, because when you're doing just an inference, you're not gonna train your model on the test set, right? So like there is no need to accumulate the gradient. So like that was the second line that usually comes in my code, which is the torch no grad, right? But like those two, essentially they stand on how you do inference. For example, could you run inference on a data set is still in model train? You could, right? But what's gonna happen is that when you do that, you're accumulating gradient and you're using just a sparse version of your neuronal network. You're not using the full neuronal network. Okay? Is that clear?
Sorry, I have a question. If we
Yeah.
make dropout from the first layer, which is the input layer, it means that we are removing variables, right?
We are removing features of this
Features.
variable. Yeah.
Uh, uh, which means that we are decreasing the space as well, no?
Right. Remember the example that I gave with the picture of a soccer ball, right? So like we said that there are several features there that are highly correlated, right? Because all the pixels that are within the ball, they're basically describing the same object, right? Do I need 10,000 pixels from within the ball to say that this is a ball? Perhaps not. Maybe with 10% of those, I already can achieve my classification, which like is just an object that corresponds to this class, right? But do I want to allow the model to use just 10%? No, right? Because there are cases where some of these features, they are perturbed. So let's say that there is an occlusion of like 50% of the ball. It's not because I have an occlusion of 50% of the ball that's no longer a ball, right? So I want to make sure that this model is able to handle different scenarios, right? So I want to regularize my neural network such that I enforce all the features to be considered all the time. And I do that by using dropout.
I was thinking similarly to the feature importance of the random forest. When a variable is removed and then its importance is evaluated. But I think the problem you evoked is more specific. For example, when you have a big data set like images, pixels, rows multiplied by columns, but when you have only a small small dimensions, like for example 10, is removing one makes sense, no?
Right.
Removing yeah.
Yeah, I think that you're talking about like when dropouts is beneficial, right?
Exactly.
And I think the answer is like when you know or you expect to have some degree of redundancy, right? Like among the features that are describing any type of sample, right? For example, if you have just 10 features, right, and they're not correlated at all, let's say that's like it's X and Y coordinates of where you have that measuring point, right? The next one is like temperature. The next one is like, I don't know, whatever other feature. They don't have any type of correlation. So like the dropout, you're actually removing one important feature that was not correlated to anything else. So there is no way to retrieve the information from that feature by using a combination of the remaining features, right? But so like in case like that, the dropout is not necessarily going to help, right? In fact, for the data set, for the tree height data set, I'm not even using dropout. I'm more introducing that as like a thing that people usually do.
Thank you so much.
Any other question? Okay. So before we go, let me just introduce this one final concept now, right? We have extensively talked about overfitting, the capacity of the model in overfitting, but we haven't properly formalized that, right? So like what overfitting usually stands for. One of the things that we discuss is still when you're talking about supported vector machine, right? Was trying to favor simplistic solutions, right? So like if you're comparing that to like a polynomial that you're trying to fit to data, right? So like let's imagine some data. The data here are these black dots, right? And what I'm trying to find is a function that fits to this data, right? Here in the first panel, right, the one to the left, I'm gonna try to fit that by a polynomial of order 1, right? So like, if it's a polynomial of order 1, essentially I'm trying to fit just a single line, right? If I try to fit a single line to this data, right, I think the best I could do is roughly like a hyperplane that looks like that, right? Sort of pass through like all the points to the best of my capacity. I can move a little bit, right? But it's gonna be a line that's roughly like going diagonal, right? We know that this sort of looks like a parabol, right? Which by all means, it's a quadratic function, right? So like ideally, my solution would find a quadratic polynomial function to fit this data, right? When I move to a quadratic function, then there you go. I have like a perfect performance there, right? Like I have this very clear function that's passed through all the points there. Does it mean that the best solution is in terms of like the best solution in minimizing the output of my model with respect to the true y, right? So like if I'm computing MSC, that's taking as input the output of my model, which is y hat, right? So that's the output of the model, and comparing that to y. This one is perfect, it's very good, right? But this one is also good because I have this function that has order 9, right? And it passes exactly through these points, as you can see here, right? By means of MSC, on the training sets, they are both equally performing well. Can you guys see this? Is it clear for everyone, right? But what might happen, right? What might happen is that these sampled points, right? They're representing an underlying system, right? So if I have points like in my test set, right? That essentially they are displaced in this curve. This one is still gonna perform well, right? But what's the performance on this guy over here with degree 9? It's gonna be terrible, right? Because you see that like the prediction of this model is going in this direction, right? So like the MSC for the test set, right? So like when I compare my test to my Y test, this is gonna be terrible. This guy is gonna fail big time, right? So what's happening here? When you have a model that is too complicated, right? Way too many neurons on it. For example, if you're talking about neuronal networks, right? This model might memorize the placement, the predictions that you have for your training set, right? So like if you're memorizing the prediction for these guys and not really trying to find like a simplistic solution that might generalize to unseen data. And that's why when, for example, you're talking about the concentric data, right? In the beginning of the lecture today, we had like a data that looks like this and then like other stuff here, right? We had that super complicated shape in the middle that looks like a star, right? Was this performing well? Yes, right? But like, it's better to favor more simplistic solutions, right? Because then they show less specificity, right, to the training set. And that generally, it's a better thing, right? When you're talking about supported vector machine, right? You guys remember that when you're dealing with a regressor, what the model is trying to do by minimize the norm, right, of the weights that describes the placement of the hyperplane, right? This thing is basically trying to just find a solution that's f of xw equal constant, right? It's like trying to find the simpler solution it can, right? Because you're trying to push for like, what's the simplest hyperplane that I could get that still fits this data, right? So like the equivalence here would be like how low can I go in terms of the order of this polynomial that I'm trying to fit, and I still get a reasonable performance, okay? Then we have these three scenarios here. One, this solution is way too simple, right? So like I'm underfitting to the data. So you see that there is a significant error, right? For these guys still. So like this is a model that's way too simple. It's underfitting because it has low capacity, right? Of like leveraging the information in my features, right? On the other side, you have a model that has way too much capacity. So like it has a very high capacity and then it starts to memorize, right? The training set. And that's when you have overfitting. What we are chasing is this middle here. So like it's the appropriate capacity, right? When you have like a good generalization to held out data set. The only way to know if this thing is actually overfitting or not is by always testing on a held out data set. That's why it's always important to like, regardless of how much data you have, to have like some data that's not used for training. It's always just meant for validation. Because otherwise, if I only have these points, right, there is no actual way for me to be able to infer if this model is overfitting or not, right? You always have to like try to see how it's going to perform for things that were not used for training. Any questions on this? Okay. If there are no questions, the next thing that you do is to do our quiz. But because it's already 8:30, maybe we take a break and we come back for the quiz and then the tutorial with the Jupyter Notebook. So if you haven't done the Git pull yet, please get your notebooks in order so we can start working on that on the second half. All right?
Yes, more than Git pull, check the wget on the Jupyter Notebook. I will paste over here. We come back at 45.
All right. See you guys in a bit. Okay. All right. So we're gonna take a quiz now. Before we take a quiz, let me say two things that I forgot, right? The first one, right after this lecture today, I'm gonna open a poll so we can start voting on the papers, right? That you guys have suggested. Thank you so much for all the suggestions, by the way. It's great to have like a lot of options. So please make sure that you vote. I'm gonna leave the poll open for you to voting as many as you want, but please restrict yourself to voting up to 2 papers, right? Because the goal is to make sure that we select the ones that have like more interest in overall, like for the people here, right? The number of papers that are going to be selected is going to be conditioned on how much time we're going to have left on the secondary lecture. Because as I mentioned to you guys today, I think it's important for us to get over the CNN part, right? Because that's like really a core concept for people who do geospatial analysis, right? So we're going to sacrifice a little bit of the time for the paper discussion, unless someone has very strong feelings about that. And please, if you do, feel free to reach out to me. Second thing, I have decided yesterday what we're going to be discussing in Matera, right? So usually the Matera week, like the lecture we have there is like a little bit of a treat, right? So like on top of the things that we have discussed, I give something a little extra, right? The previous years we have discussed like ChatGPT, for example, you know, like I think before that we did LSTMs. This year, because we also have the hackathon in Vienna, which I believe you're all aware of, right? Right? They know of that. Okay, great. So there we're going to be discussing something that's really truly modern machine learning, which is foundation models, right? It's like foundation models, they are like trained self-supervised models. So like they're not trained with a specific goal in mind, but rather just trying to leverage knowledge from raw data, right? So those are really powerful methods, and they basically are the way how models like ChatGPT are trained, right? But before we get to self-supervised, I think it's important to discuss one thing that's in between, which is unsupervised learning, right? So what I'm going to discuss in Matera is basically a myriad of methods that fall within this category of unsupervised learning using neural networks, of course. There are several other methods for unsupervised learning, PCA, K-means, and so, right? But we're going to see how we can use neural networks to do unsupervised learning. So that's what we're going to be discussing in Matera. So get pumped to it. Like, I hope you guys get excited. And okay, that's it. Let's do a little quiz. Okay, so
Sorry.
like you,
For people that are not coming to Matera, like me, would it be possible to follow the lecture as well or not?
Yeah,
I
we
think
will
so.
Okay.
have it.
Yeah.
Yeah, we will have the recording. I mean, live and also the recording lecture. Yeah.
But there is no, at the time, in this moment, there is no time schedule for Matera. I mean, it is not already.
Yeah, we don't have. I mean, it's going to
Okay.
be for the people are there. It's going to be 9 to 5, and then we will select the time slot for.
Okay.
There are going to be 2 or 3 talks, not more.
Okay, but in any
And-
case, you will post everything on the syllabus.
Yeah, the syllabus, and then the
Okay.
Thursday, Friday will be dedicated to the presentation of everybody.
Okay, thank you.
Right. It's a pity you're not coming. You're gonna miss. It's usually a lot of fun.
I know, but I cannot this time.
We
I'm
accept
sorry.
the last decision.
Okay, I shared here in the chat the link to the poll, right? Not the poll, sorry, to the questionnaire. So I want to go over like 4 questions which I think are important. Let me activate this. So we discussed these questions and then we go to the tutorial. Okay, so like you should be able to see the poll active now. You can use the QR code that's here in the corner, or you can use the link I shared in the chat. It's active, right? Don't see any answers yet. Okay,
We are 16.
great, thank you.
Sorry, I don't see it active. Don't know if you can hear me.
Yeah, I can hear you, but people said that it's active, right? Is it inactive for everyone?
It's active for me.
It's active.
Okay. Maybe
Okay,
refresh or wait.
I'll just refresh or yeah, okay.
Okay, yeah.
Fine.
Oh my God. I just noticed that I was looking at the response. Okay. I hope you guys didn't see that. I don't want any bias to be created. Okay, we have 10 answers. Okay, we have 12, right? We have 16, but 12 have answered. So I'm gonna go with 12 as the threshold. Okay, so the question was, what is an optimizer in the context of machine learning? So that's more general, right? So like in general, what's the goal of optimizer? Most people said that is a function that specifies how the loss of a neuronal network. I don't see everything, but I believe it should say like something, how the loss of neuronal network should be minimized. Something like that. Was it what it was saying?
Yeah.
Okay, great. Okay, great. So that sounds like a good answer. Let's see the other ones. B, a technique to maximize the accuracy of a model. That also has a little bit of truth to it, right? Although it's not just the accuracy, right? You could be trying to minimize some other metric, right? But yeah, by all means, B could also be correct. C, a method that processes input data. No, right? That's not the goal of optimizer. The pre-processing happens before even start training a model, right? So like the pre-processing is something that we do like the normalization step and so definitely not C. D, an algorithm that optimizes the number of hidden layers. No, right? Like there is no optimization at the level of architecture, right? That's something that we do a grid search for, but that doesn't go through the optimizer, right? So definitely not C and D, perhaps A or B. Let's see. So the answer is A, right? Although B, I could also consider as like correct to some extent, but this is a little too specific, right? What we're trying to do in terms of like the optimizer is to minimize the loss. Maximizing the accuracy is a consequence of minimizing the loss. Is that clear to everyone? Okay, great. So let's go to the next one. Activate. Okay, in a MLP, what's the role of the hidden layers? Okay, I'm gonna wait until we have 10 answers to get going. Okay, there we go, 10. So in a MLP, what's the role of a hidden layer? Let's see what people think. All right. That's a pretty big majority there. They perform feature extraction and no linear transformations. Is that right? Was there anything else going here, or was just like no linear transformations?
That's it.
Okay, great. So that's pretty good. Feature extraction and no linear transformations. Okay. They store the trained weights and biases. They store the trained weights and biases. I can see why people think that's the case, right? But like the weights and biases, they are stored throughout, right? So like that includes also inputs, right? And outputs. So like that's not just hidden layers. So like that's not entirely accurate. B, they determine the number of output classes. Absolutely not, right? By now we know that it's the output layer. So like that's not conditioning output classes. They are responsible for input data processing. No, right? Hidden layers have nothing to do with the input. Like it's truly hidden, right? So the correct answer should be C. It is C. Great. Is that clear why it's not store the trained weights and biases? Any questions on this? That should be relatively straightforward. I hope whoever chose this one understand the difference, right? Okay. Next one, 3. Should be active. Which activation function is commonly used in the hidden layers of an MLP? Oh, I gave the answer for this one earlier today, all right? So great. This one should be fresh. I see people are voting quite fast, which makes me very reassured of the result. Very good. Okay. So what's people said? Oh, we still got a little few people confused. Let's see. Okay. Yeah, the rule of thumb, like we described that there are a couple of things, right? So like there was the ReLU, which like the default one, basically. Right? Actually, it's not truly the default one. If you don't add the ReLU, the default would be linear, right? So like you could use linear too, but the overall recommendation is to use ReLU as the activation function for the hidden layers. Sigmoid is highly advised to be avoided, right? Soft max activation, we didn't even cover that because this is like mostly for classification. Okay, so like yeah, ReLU would be the correct answer. Linear you can also do, right? That would be the consequence of not adding an activation function, but ReLU overall performs the better, gives like more stability to the train. Because then you don't have like these hidden layers outputting things that goes from minus infinite to plus infinite, right? Which would be like the range if you don't have an actual activation function. Okay, so like you don't care about things that are going that far into the negative range. Okay, I think we have just one more, and then we are done for the quiz. Last one. What is the backpropagation algorithm used for MLP? All right, let's go with this. Okay, most people, we have almost a split here. What's backpropagation algorithm used for MLP? So like backpropagation is the algorithm that we just discussed, right? In the first half of this lecture, which is the way how we can compute the gradients, right? For multi-layer perceptron, right? Because we can no longer compute the gradients directly the way how we were doing before, because we have these hidden layers, like inferring what's the actual impact of changing weights in the hidden layers. It cannot be computed directly with respect to the error, right? So like we have to use backpropagation for that, which is like this chain of partial derivatives, right? So the correct answer here, updating the model parameters based on the error. Okay, that's by all means, this is just the definition of gradients, right? But like extrapolated to like multi-layer perceptron. Initialization of the network weights, no, right? That's not backpropagation by itself. Reducing the dimensionality of the input data, absolutely not. Regularizing the model to prevent overfitting. So like there are ways how we can regularize the model, which is like the dropouts, like the regularization using L2, for example, that we discussed, but that's not backpropagation by itself, right? So the correct answer is B. Okay? All good? Any questions on this? Anything that was unclear? Almost sure that was the last one. There is one more, but for the sake of time, let's just move on. Okay? Any questions so far? Let me play this. Any questions on MLP in general? If not, we're gonna start with this notebook that you should see named as Fit4 Networks, probably class 5. I think that's the name of this notebook. Did you guys find it there? Okay, great. So let's get started. Okay. In terms of like packages that we're going to be using, you're going to see that they are exactly the same that we have used for perceptron so far, right? So you're going to see our good old friend Torch there, right? Which is like the PyTorch package that we use for implementing neuronal networks, Matplotlib for plotting, SciPy to compute some stats, Pandas to handle the data frame that you have, like sklearn to do the test train split, like the metrics that we're going to be using, the R squared there, right? SciPy for computing other types of stats and so, right? Here I'm doing one thing that perhaps I haven't done before, which is to set the seed, right? That's one thing that because the initialization of weights, also the split of the data, right? Usually you have this one random seed that essentially stands for like how random is truly the initialization of things, because we are sampling from like a uniform distribution. So we are just following a distribution, but these values, they could be different every time. For the sake of like having something that's reproducible, when you're doing these splits, right, it's good practice if you want to make sure that you can replicate your results later on. Although, right, if this model is truly generalizing or like that's not too dependent on the current setup that you have, the seed should not be deterministic to say, oh, this thing is working versus not working. It's just for the sake of being able to reproduce results. Okay. So like this is not cheating. That's the only thing I'm gonna say. Next, everything that we have been doing so far has been done in CPU, right? Because like we have a relatively small model to be trained, like before was like just a perceptron. The models that you're training right now, they are still small. We're not going to be dealing with like millions of parameters, like millions of nodes in these neuronal networks, right? But as you keep increasing the size of these models that you're training, right, it's beneficial for you to be using GPUs to train your models, right? The way how you can assign like CPU processing versus GPU processing is as simple as this saying what's the device in which you would like a computation to be performed. And how we switch back and forth between GPU and CPU is something that I'm going to show you in the training script down below, right? But throughout the process, you're going to be saying like, oh, I'll allocate this computation to the device. So like if you have a GPU available for you, right? You run torch device, you can say, okay, the device from now on is CUDA, which is like the GPU, right? The default is always going to be CPU. So like unless you run this, it's always going to be CPU. Okay. All right. I'm not going to spend a lot of time in going over the data. The preprocess is exactly the same that we have used before. I'm just plotting again for the sake of like consistency, right? So like that's our data frame. We had this data frame that's originally in centimeters. We are cropping it like to 70 meters, doing the sampling. We're selecting 100,000 samples there as done before, plotting the distribution after this conversion to like meters, right? And once again, this is the model that we're trying to beat, okay? And by now we have seen that like many methods that we have explored so far, they either perform equally well to this method or we actually outperform, right? So like this is no longer an actual benchmark for us, but that's just for reference. Then we do this quick plot of the range of the features, right? We have discussed that it's always beneficial to have like some degree of normalization because our output was like super skewed to like lower values, right? As you can see here, it's nice to have something that looks like some sort of like a normal distribution in the output. So I use a power transformation for that, which in my case, I use the quantile transformer with an output distribution that looks like normal. The benefit of doing that, choose like packages like this, is that in the end, I can say that I would like to do the inverse transform, right? So I convert everything back to this type of distribution, which is the true height of trees, right? All good? Any questions on this? Okay, very well. I do the min-max on the features. So like everything now is scaled between 0 and 1, which is good because like I would like my model to start with the hypothesis that all the features, they have equal importance, right? So like they are all in the same range, although there is some skewness with respect to their distribution. We do the splitting. We are reserving 30% of the samples to be part of the test set. So we can consider that as being like a held out and do the inference for like how well this model is generalizing. Okay. I'm going very fast over that because that's something that we have seen over and over again. But are there any questions on this? No? Great. So let's get to what really matters here. Okay. Okay, so at this point, right, we have seen this like overall framework for designing a model a couple of times, right? Maybe someone can help me to explain what's going on here, right? So what's this first line doing? We saw exactly the same framework for the perceptron, right? The difference is that now I have a class, right, that I'm gonna call feed forward because that's feed forward network, right? Before it was a perceptron, but the important thing is that this is an object, right, that has the attributes of this neural network module, right, that PyTorch offers to us, right? And the benefit of having that is that it has some predefined attributes that I'd like to use, such as like the parameters, which are the weights and biases that I'm going to be training, right? And so on and so forth, right? Next, I have like a couple of features that I'm setting, right? It's like a couple of attributes that I'm setting to this class, right? One of them is the input size, and the other one, it's the hidden size, right? Before, I had output size here, right? But the output size was always equal to 1, right? Because what we're doing after all, it's a regression. So like it's fixed. I don't need to be changing the output size because what I'm trying to predict is a single value. So like it's hard-coded 1 here for in this example. Okay. So like, okay, so like now I have input size, I have hidden size. Okay. So like what's the size of the hidden layers that I'm going to be creating? Okay. And then I have FC1, so that's the fully connected. The first layer that we had exactly the same nomenclature for the perceptron, right? Which was linking input size to output size back then, right? But now we have one thing that's different, which is hidden size. So essentially, like, these are the number of nodes that I have in the input, which match the number of features that I have in my data frame that I'm going to be feeding in as the features of my samples, right? And now what's the dimensionality of the hidden layer? So like how many nodes I have in the hidden layer, okay? Then I have FC2. So I'm defining the second layer, therefore the first hidden layer, right? Here I'm projecting from hidden size to hidden size. So what's effectively what is effectively happening here is that I have two hidden layers at this point, right? That are receiving exactly the same number of nodes. So like it's just a fully connected network happening in the middle, okay? The activation function that I'm setting here is the ReLU, right? Finally, I have one last layer, which is projecting from this hidden size to 1, which is now my output layer, right? So FC3 by all means is the output layer at this point. I'm defining two other activation functions, the sigmoid. What's the range of the sigmoid?
0, 1.
0, 1. And then I have the hyperbolic tangent, which has the range of
-1 to 1.
-1. Yeah, -1 to 1, right? Okay. Now the forward. See that I'm calling that the forward. Now you guys, I was calling forward before, even if the perception, right? But now we know that there are two things. So the forward is assuming that I'm going from input all the way to output. That's why I call it the forward, right? And actually, I didn't invent the forward. Like, in fact, that's a nomenclature that everyone uses. And when you're using Hugging Face, that's like pre-established functions that you can update. So like, I would love to take the credits for that, but other people came up with this idea. Then now we have like how you're going to be processing this data, right? So like the inputs, they pass through the first connected layer, right? The first layer. And then we have a ReLU. So what is happening here? Can someone explain to me? The inputs, they go through the first layer, right? Let me... Okay. We have the input, which by all means is our X, right? We have the second layer, right? So FC1 is this guy. Perfect. Then for each one of these neurons, then we have another layer here. FC2, right? Blah, 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 blah. Lots of connections, right? Each one of these nodes here that are coming from the first hidden layer, right? They're going through an activation function. Which activation function am I using here, according to the definitions of the forward?
ReLU.
So we are using ReLU. So there is a ReLU activation here, right? Then next, we have FC3. We have defined FC3 as having like size hidden, because that's the same size that we have here, right? In output 1. So that's FC3 right there. So we have the output from FC2 going through ReLU once again. So like here we have ReLUs, right? And then finally, we have the output of the last node, right? So like this hidden goes through FC3. So we are talking about this guy over here. And what's the activation function that I'm using for FC3?
Image.
Yeah, hyperbolic tangent there, right? So what's the output that I'm expecting here? What's the range?
Range of -1 to 1.
Perfect. Okay. Everything clear? Any component of like this model that we just defined that's unclear? No?
Yes. Just a
Perfect.
question, maybe? If I may.
Yeah.
So if my output is actually binary, so I still use the ReLU for the hidden layers, and then I just use a sigmoid at the last step. Is it correct way of thinking?
If your data was binary?
Yeah, I mean, if my output has to be binary. Yeah, if my...
Right. That's right.
Okay.
Then you can use a sigmoid as output. That's correct.
Yeah.
Okay. Any other questions?
I have one.
Yeah, go ahead.
Why you split the hidden layer to 2 layers?
Oh, that's a great question. You could use more or less layers, right? If, for example, I remove this guy here, and I remove this guy here, and then I change this guy here, should be input size. By all means, what I'm doing here is to implement a perceptron again, right? But like what we're doing today is to see what's the impact of increasing the complexity of this problem. Is one hidden layer enough? Maybe. Is two hidden layers enough? I'm hoping so. Is 10 hidden layers better? Maybe, but that's something that I would like you guys to do for your homework. So what I'm doing here, it's a guess of what's the appropriate architecture for this model. But the architecture by itself, it's something that you can fine tune as well. So like by doing some sort of grid search, experiment with the architecture, okay? But that was my assumption, is that like 2 hidden layers is gonna be enough. Any other questions? Yeah, go ahead.
Sorry, just one curiosity. I was reading your code. You have written for the definition of the first hidden layer, torch dot nn dot linear. I went through the documentation of torch and found that there are 3 supplementary options like bilinear and identity, and another one called lazy linear. Okay, the question is, what's the on which basis we decide to use this one and not the other one?
Right. So I think depends on what's the property that you'd like these layers to have, right? So like the linear is implementing what we have described so far as being these vectors, right? Or in our case now they are matrices that connects input to out to hidden layers, right? So what you're trying to do is to not constrain this type of weights that you're gonna have there, right? For example, if you do like I think one of them was identity or like bilinear.
Bilinear, identity, and lazy linear.
Right. So for example, if you're trying to go for identity, right? What this is gonna try to do. So you guys know what's an identity matrix, right?
One
So
in the
yeah, identity is gonna be
diagonal.
mostly ones, right, along the diagonal, and zeros everywhere else, right? So you're saying that the behavior that you'd like to have, right? So like what I'm considering when I have linear is that these nodes, they can communicate in any directions to the nodes that are like downstream, right? If I say that I would like this to be as close as possible to an identity, I'm enforcing a behavior that's rather like this. Which by no means is something that I would like to constrain my model to follow, right? So like this is the most general type of like definition of a hidden layer or a layer in general. So like there is no reason to assume that there is a specific pattern that would like this model to have. So I can't really imagine like one case where defining these linear layers to follow like an identity would actually be beneficial, to be honest. Because if you have such a thing, right, you might as well say that like, you know what, I don't need a hidden layer. Well, what am I doing here?
It's a linear regression, basically.
Yeah, like, yeah, it's not doing anything, right? So like, yeah. Okay.
Thank you.
Maybe you do this if you're just trying to increase the number of parameters and fool the reviewers. You say like, oh yeah, I have like more parameters in my model, you know, like they're not really doing anything, but they just want to see a bigger number. So like you can do identity, yeah. Because then those are, by all means, they are trainable parameters still, right? But they're not doing anything.
Thank you.
Yeah. All right. Any other questions? I'm so sorry for like trying to push this forward a little faster, just because I don't know if I'm gonna be able to discuss CNNs today at all, but like let's see. All right. So like now we're training this model, right? So like because we have gone through this many times and I'm severely running out of time, right? I hope you're very familiarized with this structure. So like here's how we are creating the an instance of this model, right? Which like now it's part of a class called feed forward that has all these attributes, right? So the inputs is like this number of features that I have in the input, the size of the hidden layer. So see that now I'm screening through like a couple of options of like number of nodes that I have in the hidden layer. So that's how I'm gonna choose the architecture that probably is gonna fit my data better, right? Look that I'm assigning this model to be running one specific device because the instruction that I used on the top was CUDA, right? That means that my model, every time that I'm gonna call for like a forward pass in the storing of the gradients, right? Everything's gonna be happening in GPU, which is gonna be significantly faster, right? Criterion is the MSC, optimizer is the stochastic gradient descent, which by now we have our own biases and preferences, right? So like, is stochastic gradient the best option? Like maybe it's sufficient, but I would say that there are better methods out there, right? And I have my preferences, you guys pick yours. Okay, in terms of training steps, here we're gonna go over the number of training steps, which are the epoch. Every time that I start like a new pass in the training set, right? I call the model.train, which includes any type of regularization I would like to apply, right? Did I define any regularization? Not here, right? I think that the default is still considering that there is L2 norm, right? With like a default penalty associated to it. You guys can read the definition of the model there. But for example, we don't have dropout. So like there is no extra regularization happening. The zeroing of the gradients, right? That's something that we do in every training step. We zero the gradients that are accumulated from the previous training step, right? Because in accumulation of squared of the gradients, everything else, it's happening internally to the optimizer. So like, I don't need to manually keep tracking of the gradients. Like the optimizer, if I was using, for example, Adam here, right? The story of the gradients is happening automatically. So like, I don't need to accumulate gradients across training steps. So I always zero it, okay? Then the forward pass with the training set, accumulation of the gradients happens here as well. Then finally, like the computation of the criteria. Then we have the partial derivatives that are computed. So like the gradients, they're computed here, right? And then we have a step in the step in terms of like update in the weights of the model, right? Everything else is the same. Some computation in terms of like performance of the model for the training set is done here. Then finally, we switch off the training setup, right, for this model. And we stop accumulating gradients when we run inference on the test set. So like everything else is exactly the same, but with all these extra features associated to training are turned off, right? So here we just plot like the curves, right? As we have done several times before for the perceptron. Okay, let's look at performance, okay? Okay, so I think that the best model that was performing for the like using perceptron was something around 0.43 or so. Yeah, 0.43, right? So like that's essentially like our reference now. Why did I lose the thing? Okay, there. So you see that the very first, even like with a high learning rate, right? So like, let's keep in mind what has changed. Very high learning rate, 0.75, right? Remember that with high learning rates, some of these models didn't even train. Like even using Adam, right? Which was the second half here. So here we're using Adam. So like we had a pretty big learning rate, 0.5, right? But it already had some instabilities here as well, right? Here we do have some stability still going on, but you see that overall, the performance of this model is already better, right? We are like already reaching 0.51, right? It's increasing our value by 0.1. That's a significant increase in our value, right? In terms of stability, you see that it's not extremely stable. In fact, you have this huge spike for the validation loss, at least around like 2,500 epochs there, right? After that, there is a little bit of instability, but it eventually starts to become more stable again, right? There are two signs here that we can observe. So like first, we are using stochastic gradient. Were those balloons that I put in the back? How did I do that? So like, so we had this a little bit of instability, right? That's being generated. We now have a couple of things to be explored in terms of addressing potential instabilities. What would you guys recommend as ways to mitigate instability here? Get something that looks more like a stable training curve. I'm so sorry, I had a hard time to hear you. Can you repeat that?
Changing the learning rate.
I think you're suggesting reducing the learning rate. Yeah. Reducing the learning rate. It's essentially what we're gonna try attempt next, right? So that's like the number one thing to be tried. On top of that, you could also try a different optimizer, right? Because the one that we're using right now is stochastic gradient, right? So like by now we know that stochastic gradient is not the best one for that, right? Because if we start with a very high learning rate, there is no adaptation of the learning rate, right? But let's see what happens when you just reduce the learning rate. So I go from 0.75 to 0.5. Okay, it actually gives me a little bit more stability, like around the end, right? It was oscillating way faster here, right? It becomes slightly more stable. That's a little better, right? And that already reflects some impact also on R value. So it went from 0.51 to 0.52, right? Not huge difference, but like reasonable enough. 0.1. Okay, this is getting quite stable, but at the cost of not converging within 10,000 training steps, right? You see that there was still quite a bit of room for like improvements in this model. So 0.1 sounds promising, but what should you do if you want to stick to 0.1? What should we do if we want to use this one? Train for longer, right? Okay, great. So one thing to observe, right? So like, let's assume that this curve was still going this direction and this one was going this direction. So like, this is something to keep track of, right? What's this gap that we're observing here? If we start to see something that looks like this, okay, this is showing some signs of overfit, right? So like, make sure that if you're gonna train for longer, you don't get like just improvements in the training, but also the test, right? Make sure that this is not exploding. Okay, clear? Okay, then even smaller learning rates, you see that like, yeah, this model is having like a hard time. This one specifically even start to show some signs of getting stuck in a local minima, right? You see that it wasn't changing as fast anymore, but at the same time, it was kind of plateauing, but in a very high error still, right? Compared to what we have observed before. Like this was seen 0.46. All right, no convergence, no convergence. Okay, so here we changed the size of the hidden layer. Before it was 128, so now we have more neurons in the hidden layer, right? More neurons in the hidden layer with very large learning rate, right? We are closer to this setup that Severio was trying earlier today, right? So like, yeah, I have a bunch of neurons in the hidden layer, but like I only see that this model converges relatively well when I have a large learning rate, right? And that seems to be the case that we're experiencing here too, right? Keep in mind that these lines, they look thick, but in fact, they are like tiny tiny oscillations that are happening there, right? So this optimizer is still moving around, but kind of like around the global minima there, which is a good thing. It's still allowing some degree of exploration, but very locally, right? And then we have 0.52, which like relatively good performance there. Decreasing a little bit the learning rate, even better, 0.5271. So like with tiny bit of instability there, but not too bad. Once again, decreasing the learning rate, like didn't allow convergency, but this was looking pretty good, like 0.51, right? With 10,000 steps, with a lot of room for improvement. So this was trailing the right direction. Okay, what time is it? 9:30. Oh God. All right, so we have many other examples here, right? Like that you can play with. And you're gonna see that, yeah, overall, there is a little bit of hyperparameter search that needs to happen, combinations of like number of neurons in the hidden layers, right? Versus what's the learning rate that's best fit for that specific configuration. So like every time that you change the architecture, the learning rates that you need, right, might change as well. So it's very hard for you to say like, oh, I'm going to stick to one learning rate and then just change the architecture, right? They kind of have to go together as well. So all those things you want to be optimizing jointly. This other example here, there is one difference, right? Can you guys spot the difference for like this other model that I'm training? I think you're talking about an extra hidden layer that I'm adding there. Right, so you have two extra hidden layers that are being added to this model, right? Everything else is being kept the same. So like the range of learning rates that are being explored and the number of neurons in these layers, right? So let's just take a quick look at the outputs. 0.51, 0.45. Notice that, for example, learning rate of 0.5 and hidden layer 128 was performing relatively well before, right? With a little bit of instability. Now it became quite unstable, right? You see that there is like a lot of oscillation happening here. The performance is not terrible, but like lots of oscillation happening. Let's see another example. Yeah, so like overall, one thing that to observe is that there is quite more instability happening here, right? And these models, they're like taking longer to start like dropping the loss, right? So like that's another thing that you have to keep in mind as well. So like in cases like this, you might consider like larger learning rates, right? Or there is another thing, like for example, you just keep increasing the complexity of the problem, right? And you see that increasing the number of hidden layers actually brought more harm than good, right? So like always increasing just the complexity of the problem, not necessarily is a good thing all the time, right? So that's also something to keep in mind. Favor like simpler solutions. It's always a good practice. Okay. I'm just gonna go over these very quickly just to make sure there was nothing that was worth discussing here. But essentially what we're doing is to change the number of hidden neurons in the hidden layer and the learning rates that you had. So like these by now you guys are very familiarized with. Okay, here. This is something worth discussing. So we have implemented our own neuronal network. Our own neuronal network using PyTorch, right? Before, when you were doing support a vector machine, we use the implementation that was available through sklearn, right? sklearn also has its own implementation of MLP regressor and the classifier, right? So for example, if you're doing regression, we can use sklearn for that, right? The MLP regressor, let's take a quick look on its definitions there, right? So like the things that you have control over, it's hidden layer sizes. So like in terms of input, there is no need to set the input because that's going to be proportional to the number of features that you have in the inputs that you're feeding, right? So like that's going to be set automatically. But the number of neurons that you have in the hidden layer are going to be dictated like this. So like it assumes that you have at least one hidden layer with size of like 100, so 100 neurons in the hidden layer. And if you keep increasing the number of parameters that you're passing to hidden layer size, that's basically how many more hidden layers you'd like to add, right? Activation function, the default, it's a ReLU, right? You can control also like the optimizer that you're using, the learning rate, and so and so. Yeah. Actually, alpha here, it's sorry. So you guys remember that there is the alpha and the beta for Adam, right? Which are basically like these coefficients that give you the exponential average decay over the learning rates, right? And how you keep information of how you consider the squared gradients throughout the process of like adapting the learning rate, right? So that would be the alpha for the MLP regressor. The learning rate here, it's a number that you can pass directly like this via the learning rate parameter, okay? You can set the warm up and so like number of iterations. So like that's essentially how you set the number of epochs, right, that you have. Very well. Number of iterations here, we're using 1000 iterations, right? You can define the random state. That's for the sake of reproducibility. So how you initialize the weights of your model, right? Before, the way how I was controlling that was by setting the seeds, right, for PyTorch, as I discussed in the beginning, okay? Okay, so you see that like for hidden size, I'm using the default, right? Because I'm not specifying. So like I'm using just one hidden layer with 100 nodes on it, right? The way how I fit this regressor is the same way how we did for SFDM. So like I define an object that has these properties, and then I say fit that to the training data that has like some features and some target labels associated to it, right? After I have fit it, I can just run the prediction and obtain a plot that looks like this, which is like by all means, right? Although we haven't inspected the loss, right? Like this, you do have access to the loss as well. So for example, one of the objects that are returned from the training is the loss curve. So like if you call for this regressor that you just fit here, right? Like dot loss curve, you obtain plot vectors that are essentially going to give you the same information that we have obtained through my training script, right? But in terms of like R value, the performance is relatively good, right? Keep one thing in mind, like one huge disadvantage for MLP regressor is that everything that's done through sklearn, right, is done in CPU, right? So if you're trying to analyze a ton of data, this is extremely slow, right? So one thing that I would say that's good about using the MLP regressor is that it's a very nice way to troubleshoot architectures, depending on the problem that you're dealing with. If you have a really large model that you're gonna define through sklearn, this is gonna be way too slow. So like that's not worth doing it. So like I would say that overall, the best approach is to use PyTorch, right? Here I have increased the size of this model by increasing the number of neurons that I have and using 3 hidden layers, right? And you see that with the same number of iterations, like 1000 still, right? We did not converge. So like this is still looking like just a Gaussian distribution, right? So this model needed to be trained for longer and perhaps with like a larger learning rate as well, right? Okay, just to summarize what we have seen so far. Okay, just to summarize what we have seen so far. We have seen the implementation of multi-layer perception using PyTorch, right? With all these different layers of flexibility or things that you can upgrade in your models, like number of layers that you have, the size of these layers in terms of the neurons that could incorporate that. Other things that perhaps we could make better in this model. I think the very first thing that I would do is to use a different optimizer, right? Other things that could be done, different activation functions, different normalizations of the data, right? So like that being different power transformations. I use the quantile. There are others, as we discussed in the previous lecture, that could be beneficial as well, right? And so on and so on, right? So like perhaps what we could do as like the assignment for this lecture is to play with all these different hyperparameters that could be optimized. And now I leave to you guys the task of perhaps trying to obtain a model that performs better than 0.52, because apparently that is the new gold standard now. 0.52, yeah, at least more than 0.52, okay? All right. As usual, it's already 9:38 and I haven't got to the second half of my lecture. The goal was to start CNNs today. Did not happen. So I think we can compromise by doing CNNs in the beginning of the next lecture on Thursday, and then discussing perhaps 1 or 2 papers maximum in the second half. And then we call it like a semester of ML. for geospatial. What do you guys think about it? Does it sound good? Or you guys want to just leave behind the CNN part? Although I think it's very important, but if the crowd thinks it's better to discuss just papers, I'm open to considering it.
Yeah, let me the CNN convolutional neural network is quite important in the spatial science because it's considering also the surrounding of your feature present. So if you have a point location, it's also looking what is happening in the surrounding. So that's why it's quite important.
No, yeah, I agree.
Spatial science.
And
so to have it, and in case we want to discuss paper, we can also add in a discussion, 1 hour discussion when we are in Matera next week. So
yeah, and I hope you can contemplate that what we're doing here, right, is essentially to discuss the building blocks for what most of the methods that use neural networks they use, right? So like most of the things that you're going to see implemented out there, they're built on these concepts that we have discussed here, right? And even CNNs, you're going to see in the CNN lecture that what we're doing is essentially just change the arrangement on how we are considering the input features as having like some spatial organization to them as well. So far, we are assuming that each one of these features that we're taking as inputs, they don't have any sort of like local dependencies in between them. They might have some linear relationships, codependencies there, right? But there is no actually relevance on like where these features are placed. So like neighboring features, right? If there are two columns next to each other, there is no reason to assume that they have some sort of dependency, right? But when you move to like spatial data, now that becomes a norm, right? Where like neighboring pixels, usually they have similar information, right? So essentially it's just how we're considering what type of like biases we have with respect to the organization of these features, right? And most of the things that are gonna come later on, like LSTMs, transformers even, right, is essentially how you leverage information about the placement of these features, right? But the concepts are exactly the same. Everything else is more like assumptions about the nature of the data. Okay. Okay, so maybe we stop here and then we resume next lecture with CNNs. And second half is gonna be paper discussion to the best of our capabilities. I'm gonna open the poll for voting the papers that you guys have suggested. And then by the end of the day, okay, so like I know that's kind of getting late for you guys. What time is it there now? It's like 4 p.m.
4 p.m.
Okay, yeah. So like please try to vote that before you go to bed today, right? So like the people that suggest the paper, they can prepare the introduction of the paper as we have discussed. Okay? Deal?
Okay, good.
Can I count
deal.
on you guys to vote? Yeah, cool. I'm gonna enable the poll in a little bit and I send a message on Discord so you guys can start voting. All right?
Okay, thank
All
you
right,
very
guys.
much.
We talk later.
Bye
Bye.
Thank you. Bye.
From our side, I'm going to sending an email about the organization of next week. That there are going to be information for the material in general, but also for people that are attending online. Okay, and some tips about the organization of presentation, how to present, and so on. Okay, all the best. See you in 2 days.
Thank you.
See you.
See you. Bye.